you come up with a situation that SBW is equal to lambda SWW. Yes? And that means SW inverse SBW is equal to lambda W. If you multiply SW inverse both sides, this is just a scalar, this goes away, this becomes an entity in this. Yes? Yes. Because I multiply SW inverse both sides. So यहाँ पे ये scalar है तो scalar by आ सकता है. Once the scalar is out, SW inverse times SW is simply identity matrix. This goes away. Here we have SW. Yes? If I call this matrix as A, W as X, then this is eigenvalue problem.
Yes.
Find out eigenvalue and eigenvectors of SW inverse SP. Remember, SW you have computed from the data. SP you have computed from the data. Now SW by inversing SB से multiply करें, you will be having a matrix. उसके eigenvalues और eigenvectors निकालें. Make sense? अब सवाल ये है कि कौन सा eigenvector? There are several eigenvectors of this matrix A. Which one? PC में हमने देखा था that eigenvector happened to be an eigenvector corresponding to the largest eigenvalue. अभी हम देखते हैं कि which eigenvector to pick. There are several eigenvectors. Remember we have to maximize this. So we have to pick the eigenvector that maximizes this. Make sense? So eigenvector has to be chosen with respect to the eigenvalue.
Yeah.
But which eigenvalue? Smallest to largest or some middle point, whatever. What? Make sense? So let's see that. So far so good?
Yes.
So SW is computable from the data, SB is computable from the data, SW inverse SV is just computable from the data, computers, eigenvalues and eigenvectors, you know all of them. Now you want to choose which one. Make sense?
Yes.
Great. If you see this one, I'm writing this here. SBW equals to lambda SWW. And if you multiply both sides with W transpose, you are just okay.
Yeah.
Yes? And if you divide this number here, you get W transpose SBW over W transpose SWW equals to lambda. Because you want to maximize this, that means you should take the value that is the maximum. What you want to maximize happen to be the eigenvalue. I have not constructed it, it just happened to be an eigenvalue. Now because you want to maximize, जो criteria maximize करने जा रहे हैं, at the end of the day is an eigenvalue. सही है? Because you want the max of it out of some number of eigenvalues, pick the eigenvalue that is the maximum. Correspondingly, जो eigenvector होगा, that is going to maximize the criteria. So the algorithm is very simple. Compute SW, compute SP, then compute SW inverse SP, compute its eigenvectors. Pick the eigenvector corresponding to the largest eigenvalue. Why? I have proven it that this is the one that is going to maximize the criteria. Yes, no? Yes. Make sense? Now this was for two classes and one-dimensional projection. Now what if we have multiple classes and multi-dimensional projections? How to move? Make sense? Yes, no? अभी भी आप ये एक सवाल कर सकते हैं कि अगर d dimensions थी, two classes में रहते हैं, अगर d dimensions थी, classes दो ही हैं, तो दो classes के अंदर रहते हुए multi dimensional projection नहीं हो सकती। मैंने two classes ली हैं और मैंने कहा मैं one dimension में project करता हूँ। Original dimensions थी 100, डेटा की ओरिजिनल डायमेंशन थी 100। तो आपका ये सवाल होना चाहिए सर अभी फिलहाल क्लासें 2 ही रखें, जरा 10 डायमेंशन पे प्रोजेक्ट कर देते हैं, 100 से 10 पे भी तो आ जाएगी ना। नंबर ऑफ क्लासेस बाद में पढ़ाते हैं। यस, इट टर्न्स आउट that this matrix, this one, this is a little involved effect, and I will not go into the detail of it. This matrix has, यानी ये जो matrix है ना B S B, इसका rank 1 है। ऐसा क्यों है? पहली बात तो ये है कि ये एक वेक्टर है, at the end of the day it's a vector, और ये उस वेक्टर का ट्रांसपोज है। सो वेक्टर एक वेक्टर जो होता है कौन सी वेक्टर हो तो उस वेक्टर का रैंक 1 होता है। अगर मैं वेक्टर को एज अ मैट्रिक्स देखूं, एक वेक्टर तो उसका रैंक 1 होता है। दो रैंक 1 मैट्रिसेस अगर मैं मल्टीप्लाई करूं तो द रिजल्टिंग रैंक इज एट मैक्स 1। सो इस मैट्रिक्स का रैंक तो 1 है, लेकिन दो मैट्रिसेस ऐड हो रही हैं, ये भी रैंक 1 है, ये भी रैंक 1 है, ये दोनों ऐड हो रहे हैं।
तो फिर रैंक 1
जब दो मैट्रिसेस ऐड हो तो उनका रैंक ऐड हो सकता है, रैंक कम भी हो सकता है, यानी रैंक बढ़ भी सकता है, कम भी हो सकता है। Addition of two matrices can have larger rank or smaller rank depends. In this particular case, the rank stays 1, and the reason it is a little involved, और reason ये है कि ये जो point है, अगर मैं इसको data point consider करूँ, ये अगर ना समझे तो that's okay. अगर मैं इसको data point consider करूँ और इसको भी data point consider करूँ, तो मैंने इसमें से भी mean subtract कर दिया, इसमें से भी mean subtract कर दिया। तो अगर मेरे पास दो पॉइंट्स हों, दोनों इंडिपेंडेंट हैं, और अगर मैं दोनों का मीन लेके सब्ट्रैक्ट कर दूं, तो एक पॉइंट में दूसरे की डिपेंडेंसी आ जाएगी। The rank will become 1 less. That's okay if you don't understand. The result of this is this matrix SB has rank 1 because it is the sum of two matrices. One of them depends upon the other. B1 depends upon B2, B2 depends upon B1. मैं आपको सिर्फ ये बता दूं कि अगर मैं आपको B1 दे दूं, you can construct B2. अगर मैं आपको टोटल मीन दे दूं और क्लास 1 का मीन दे दूं, तो आप क्लास 2 का भी निकाल सकते हैं।
अच्छा ठीक है,
मेक सेंस?
उनके हमें ये पता लगा कि इंटरेस्ट पॉइंट्स ऑफ कोर्स।
So one matrix depends upon the other. Hence, because the rank of SB is 1, the rank of this product is 1. The rank of this, the product is just 1. अगर दो matrices में मल्टीप्लाई करूं, उनके जो रैंक्स हैं जो भी हैं, the resulting matrix has rank at max the minimum of all the matrices in the product. तो matrix अगर 4-5 matrices आपस में मल्टीप्लाई हो रहे हैं, तो मल्टीप्लिकेशन का जो प्रोडक्ट का रैंक क्या होगा? जो मल्टीप्लाई होने वाले जो matrices हैं उनमें से जो मिनिमम रैंक वाला है, at max प्रोडक्ट का रैंक उतना हो सकता है, उससे कम भी हो सकता है। कम भी हो सकता है। Yes, and in that case, this matrix has rank 1, which means there is only one eigenvector that has non-zero eigenvalue. All other eigenvalues are 0. So you cannot project in more than one dimensions if you have two classes. And we will extend that result when I will introduce multiple classes. If you have 10 classes, the maximum rank of SB is 9. And you can only project to 9 dimensional space, not more than that. And this is a drawback also. If you have a binary classification problem, you have two classes, and you have original dimensions are, let's say, a million. Original dimension is a million. But just having two classes means whatever projection you are coming up will be one dimensional. It will project a million numbers to one number. Make sense? And it is sometimes very hard to still hope a better discrimination. So there are certain assumptions under which this discrimination happens, that those assumptions I have not described. Just for a theoretical note, the assumptions are the original data is multivariate Gaussian with equal covariances. If the original data does not have this property, then the Fisher linear discriminant they give very degraded results. Make sense? So it should not be applied blindly, although it is applied blindly. But sorry? Actually, जितनी आपकी क्लासेस हैं -1 पे, अभी मैं मल्टीपल क्लासेस में जा रहा हूँ, लेकिन होगा ये जब मैं मल्टीपल क्लासेस में जाऊँगा तो इस तरह के कितने मैट्रिसेस ऐड हो रहे होंगे। For alpha 1, alpha 2, alpha 3, let's say 10 classes हैं, तो 10 matrices ऐड हो रहे होंगे ना, between class कैटर के लिए, उसमें से एक matrix dependent होगा, बाकी 9 independent होंगे. So rank होगा 9, so 9 dimensional subspace पे आप प्रोजेक्ट कर सकते हैं, बाकी सारी एक ही वैल्यूज की होंगी. सही है जी? But let me go towards the derivation of multi-dimensional case. If this is okay so far, is that okay? Yes, no. Are there confusions? I've skipped some details of rank and stuff. If that is hurting you, that's okay. You can cover it outside the class.
ठीक है.
Okay. Having believed the fact that this is rank 1, that there is only one dimensional projection available. Clear? Okay, multi-dimensional case. Erase कर लो? Yes, sir. Let us define the within class vector for multi-dimensional case. In the multi-dimensional case, we have W1 transpose xi, and that is alpha I1. Then we have W2 transpose xi1. Let's say xij of class J. ठीक है जी? Jth class के लिए. So this is alpha I2 of class J and so on. So Wk transpose xij, that is alpha I k of class J. This is rather than one real number, because now you are using k directions, find out a subspace, smaller subspace, that maximize the Fisher criteria. But now we have to define the within class scatter and between class scatter and different. In the same way, but the criteria will not be like very simple criteria. It will be a different one. So yes? Okay. Now, पहले आप क्या कर रहे थे? Class 1 का अगर मैं S1 compute करता था, remember S1? पहले S1 ये था. It was I is from 1 to n1. xi1 minus x 1 bar times xi1 minus x 1 bar transpose. Yes?
Yes.
This was S1. अभी भी S1 यही होगा. सही है जी? लेकिन मैं थोड़ा सा डिटेल में चला जाऊँ, थोड़ा सा अगर इसको डिटेल में एक्सप्लोर कर लें, तो थोड़ी सी चीज़ें कुछ चाहिए तो देखनी थोड़ी सी ज़रूरी है. टाइम तो हमारे पास है. Let's see. Okay. Now our goal is the following. Let me find alpha I j to be a vector of this. Make sense? Okay, class 1 scatter. Class 1 scatter is the following. It is alpha I j minus alpha j, class j का scatter. Now it is no longer a square. It is no longer a square now. It's a vector, it's a norm. And this is for all the points 1 to n j. Class j. This is this is the variance j. This is the variance of class j. Yes? This is the variance of class j. And we want the variance, the total variance is simply j varies from 1 to
Classes.
c, now total number of classes. That's total variance. Except this is the variance of class j, this is the total variance, and we want to minimize the then class variance.
Yes.
Yes?
Yes.
The between class variance is the following. इसको मैं एक्सप्लोर करता हूँ, अनरावल करता हूँ. The between class variance is the following. Alpha 1 minus alpha, let me write this between class variance in the following way. J varies from 1 to c, alpha j bar Make sense?
Yes.
This is the between class variance, this is the within class variance. Yes? Okay, now I'm going to unravel this. If I write this, by the way, this derivation is not very straightforward, it's not very simple. If you have projector, I have this derivation available in my slides. I can show you quickly that you need not go through that hairy kind of derivation, that the derivation is very involved. But I have that derivation available in my slides with bit by bit details. So, I will show you, I will share that document with you, those who are interested, but it involves several things that you might not know, that you may not know already. Make sense? At the end of the day, this thing will appear as trace of W transpose SWW, where W is the following: W1, W2, WK. This is the matrix W, and SW is the same as SW is S1 plus S2 plus SC, and S1 has the same definition as before. Make sense? So this is trace. This is a matrix. By the way, this W is D by K because we have K basis vectors. Each has K dimensions. So this is K by D. This is D by D. This is D by K. So this inside is a matrix K by K.
Yes.
This is no longer a number. So we cannot write a matrix over matrix. However, trace of a matrix is a number. And it just so happens that if you open this up, this becomes trace of this. Make sense? And similarly, if you open this thing up, it becomes trace by the way, trace of a matrix is just the sum of its diagonal entries. Trace of a matrix is the sum of its diagonal entries, and that's a number. This becomes trace of W transpose SVW. And your goal is now to maximize this, where W is defined like that. Make sense? Again, this SB again will be having rank C minus 1. So the maximum number of eigenvectors you will pick, इसका भी solution आपको मुझे पता होगा, it happens to be eigenvectors. The maximum number of eigenvectors you come up with is C minus 1. Make sense? So अब यहाँ पे ये नहीं है कि 99% आपने करना है, 98% करना है as contrast to PCA. It gives you a definite number of vectors to pick. Make sense? Number of pluses minus 1. Okay. Just some notes about this. This is called ratio of traces, and this is not convex. Clear? This is not convex, so people have a relaxation of this criteria, which is trace of ratio. This is ratio of traces. So ratio of two traces. People come up with a criteria called trace of two ratios. Trace of this. This is trace of ratio. This is non-convex, this is convex. But this, the result of this is suboptimal. I mean, do not consider case A2 job resulting that is completely optimal. So in the multi-dimensional case, the global optimum is not achievable directly. So people come up with this criteria, and the division of a matrix can be written as W transpose SWW inverse W transpose SVW, and then you find a trace of this. Make sense?
Yes.
और काफी सारे लोगों ने इसको डिटरमिनेंट के फॉर्म में लिखा होता है, जो मेरे नोट्स हैं उसमें मैंने तफसील से बताया कि ट्रेस को डिटरमिनेंट के फॉर्म में लिख सकते हैं. There is a derivation in that. That's a hairy kind of derivation, but it is there. Clear? And then solving this, इसका solution भी मैंने करके दिखाया हुआ है नोट्स के अंदर. Solution is not simple. I'm not going to explain that in class. But the solution turns out to be the following: SW inverse SVW is equal to W lambda.
Okay.
अब जो ये मैट्रिक्स है, ये जो मैट्रिक्स है, तो ये लैम्डा का भी एक मैट्रिक्स every vector of W is actually the eigenvector of this matrix. This is the solution even if you don't know the derivation. So compute SW from the data, compute SB from the data, compute SW inverse SB, and compute all the eigenvectors. Pick all the eigenvectors that are non-zero, that corresponding to non-zero eigenvalues. And they are at max C minus 1 of those. Project to those and they will discriminate the max. Make sense?
Yes, sir.
I have written several details, but these details are there in my tutorial that I've given. Actually, I've given that tutorial to machine learning MPhil students in March 2018. That is very small tutorial. It has a lot of math and all the derivations, bit by bit derivation. I've shared that tutorial in teacher data. I will send it as an email to you as well. Make sense? In all that derivation, one step that we have absorbed without thinking a lot is, what if SW is not invertible? See, this derivation depends when SW is indeed invertible.
Yes.
What if SW is not invertible, it is singular? Then how to, then SW, if SW inverse is not possible, then how to move? And in most of the cases, SW is singular. And those kind of problems are referred to as SSS, small sample size problems. If your data points are very small and each other high, then SW will be singular. And in that case, there are two solutions. One is regularization. Regularization means you pick SW and you add a very tiny number times identity to it. And that makes SW invertible. That kind of, so you have to pick a particular number, gamma, appropriate number that is better for classification. So you have to cross validate for gamma. This is one solution. The other solution is null LDA, also called null Foley sum transform. That's a relatively advanced concept. It requires no cross validation. The idea is very simple, very intuitive. You pick certain vectors of SW and you just discard those and reconstruct SW in a way. In fact, to be very precise, if you don't understand what I'm going to say, that's okay. But this is the precise argument. You come up with the vectors W that are in the null space of SW as well as in the row space of SB. And those vectors can be found in a closed form. And they maximize this criteria. Make sense? So it does not require any regularization. If you don't understand this, that's okay. There is a paper in CPR 2016, Learning Discriminated Null Spaces for Personal Identification by Zhang. It's a very good paper. You can go through that paper and you can understand the stuff more. But the idea is the following. This is a matrix. You can find out its null space, row space, everything. Find out the null space of SW. That is also the row space of SW. And in that way, you do not need regularization and you can find out the optimal result. Make sense? And this result is called a null LDA, also called a null Foley sum transform. Make sense? Having, sorry? Null LDA is find out the null vectors of SW that is in the row space of SP. So find out the common space of row space of SP, find out the intersection of row space of SP and null space of SW. Pick those vectors. Make sense? Okay, having said that, that's the end of classical machine learning. Inshallah, from Tuesday onwards, we'll start neural networks. And to start neural networks, I request you to go through logistic regression again. Because this is the logistic regression that is there in neural networks everywhere. Clear? Okay.
Concept is pseudo inverse होता है. तो मैटलैब में एक टर्म होती है कि आप सिमेट्रिक से अगर इन्वर्स नहीं निकाल पाते वो सिमिलर है तो उसका अप्रोक्सीमेट pseudo inverse आप निकालते हैं.
ये वही तो नहीं?
Yes, there is a method of pseudo inverse, but that involves total scatter matrix ST rather than SW. There is a total scatter matrix also. And there is a paper by Alok Sharma, 2012, he explains that Alok Sharma and Gilbert Strand, वो paper Gilbert Strand ने
अच्छा।
वो किया हुआ है, and they have proven actually you can use pseudo inverse as well. But उनका जो पेपर है वो ये है कि pseudo inverse use करने से computational complexity हाई हो जाती है, तो एक random matrix use करते हैं to do that. But I'm not sure people have used SW का pseudo inverse, but S total scatter matrix, SP का pseudo inverse people have used, and that is an approach. Yes.
एक और सुना था कि हम जब ये डिस्क्रिमिनेशन ये करते हैं, सो हम देखे थे कि लाइन कम होने की वजह से क्लास रिड्यूस
Number of vectors reduce होता है.
नंबर ऑफ वेक्टर्स
Dimensions तो आपकी number of classes उतनी रहनी है. पहले आपका डेटा 100 dimensions था, अब आपका डेटा 9 dimensions पे आ गया. डेटा 9 dimensional labels तो वही रहे हैं. So this dimensionality reduction is a pre-processing step, then classification. Classification इसके बाद होनी है. This अगर आप FLDA वाली pre-processing करेंगे, तो the chances are कि आपकी classification शुरू हो जाएगी.
सो ये जो j is equal to 1 to c तक का जो ये सबमिशन है,
Yes.
एक्चुअली डायमेंशन है.
No, these are not dimensions. These are not dimensions. J is equal to 1, C is not dimension. Dimensions are k. I have k dimensions. C is not dimension. These are the total number of scatter matrices. And for each class, I have a scatter matrix. Make sense? Actually, the total number of dimension might be much lesser than C minus 1.
अच्छा।
Yes. This is the maximum number C minus 1. It may be lesser than that. Okay, let's see you on Tuesday. Yes. Question. Better. जी.
वो मैक्सिमम ट्रेस वाला लिखा हुआ है
Yes.
उसके बाद नीचे आपको पहले वाइट भी ट्रेस है तो ये कन्वेक्स हो
ये convex है.
उसके बाद ये नीचे वो आपने नल एनबीए वाली कुछ सेटिंग्स है
वो मैंने तब यूज किया है जब SW में वर्टिकल है. और ये पूरा पेपर है ट्रेस रेशियो और रेशियो ट्रेस पे. पूरा पेपर है CBR 2007 पे. पूरा पेपर है सॉल्विंग ट्रेस रेशियो विद रेशियो ट्रेस. आई मीन उन्होंने पहले प्रूव किया है कि the ratio of traces it is not convex. Then they show that the trace of ratios it is convex. Then they come up with an iterative solution that find out the global solution of the original problem. Global solution. लेकिन वो iterative है closed form.
तो जो आपको एनिमेशन की बात है जो स्टाइल वाली तो वो मैसेज करने की जरूरत तो नहीं है पेपर के लिए पेपर के मतलब
हाँ जी है.
वो सारी एनिमेशन
But even more कुछ practice files में मज़ीद आएंगे जो हमने क्लास में की. Okay, let's see you on Tuesday. By the way, let's see you on tomorrow. I have Viva with you. You have Viva with me tomorrow, and then officially in class on Tuesday.